Okay, so section 5.1 is all about being able to identify a linear function. We're going to be living in linear function world for most of second semester and the rest of this semester. And then we'll move into other types of functions, specifically quadratics. So by the end of today, you should be able to identify linear functions and linear equations, and you should be able to graph linear functions that represent real-world situations and give their domain and range, which we have already done. Why do we care? Well, linear functions can describe many real-world situations, such as distances traveled at a constant speed. So a function whose graph forms a straight line is called linear. So if we have a graph that is a straight line, then we identify that as a linear function. So here's our first example. Let's decide whether the graph represents a linear function or not, and explain. So A, is it linear? Well, first, I guess, is it a function? Yes, it passes the vertical line test. Is it linear? Yes, it's a linear function. Passes, and write vert line test, and is a straight line. Ran out of space. Hopefully you can fit your stuff in there.
I need to move. It smells so bad.
So for B, is it a function? Okay, can we just stop talking? B, is it a function?
No.
Does it pass the vertical line test? Yes, it's a function. Is it linear?
No.
Not linear. Oh, yeah, sorry. I'm zoomed in too much. That should be B. So, yes, it's a function. Not linear. So, no, it's not linear. Not a straight line. If we look at C, is that a function? What do we say about up and down? It's not a function. It doesn't pass the vertical line test. Because it is a vertical line. Right, guys, please be quiet. All right, so see if you can do the bottom three on your own. Go. So say yes or no whether it's a function, and then say yes or no whether it's linear. So you should have two parts.
The first one
Don't
is
shout
yes,
out.
And the two other ones are no.
Don't shout out. All right, let's check your results. Number A, 1A. Is it a function? Yes, it's a function. Is it linear? Yes, linear. Good. For B, is it a function? Yes, that does pass the vertical line test.
Yes.
Is it linear? Yes. It's a straight line, isn't it? For now, 1C, you just put it there. Thanks, Charlie.
No.
Not a function. Yeah.
No.
Horizontal lines are okay. It's not a function. Yeah. Vertical lines are not functions. Horizontal lines are. Okay? Alrighty. Flip on to the next page. Bless you. So now you can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, you're going to have a constant change in both your x and your y's. So, for example, in this table of values, my x's are -2, -1, 0, 1, 2. They are increasing by 1 each time. and my y's are decreasing by 3 each time. You see that? So in this table, it says a constant change of +1 in the x corresponds to a constant change of -3 in the y. So this would satisfy that it is a linear function. If I were to actually plot these points, it would end up looking like a straight line. Okay? Let's look at one that doesn't work out that way.
What page are we on? Oh, this one.
Hold on. Okay, so back to it. Over here in this table, notice I have a constant change of +1 happening on my x's, but then what's happening on my y's? Well, 6 to 3, it's minus, it's all over the place. So -3, -1, +1, +3. So that would not be linear. If I were to graph it, you can see how it would make a U shape, which is quadratic. Okay? All right, so let's work through this one on our own. Well, not together, not on our own. So here we have 2, 5, 8, 7. So what's happening from 2 to 5? Adding 3 from 5 to 8. Adding 3 from 8 to 11. Adding 3. So the x's are good. Now let's check the y's. 4 to 3. -1. -1. -1. So is it linear? Yes. So yes, linear. That's all we need to do.
Yes.
We could think about the rule itself, right? What's happening if I had to come up with the rule? How do I go from my x to my y's? I guess I can't really figure that out. It's kind of hard, huh? From 2 to 4, we're adding 2. From 5 to 3, we're not adding 2. So that rule would be a little bit complicated. Let's go down to B. What's happening to your x's each time? Adding 5. So we're doing a +5 each time. But then what's happening to your y's? We're subtracting 6, subtracting 2, subtracting 2. So is that constant?
No.
So not linear. Okay? All right, so see if you can do this one on your own. Here it's not in a table of values, so you can either put it into a table of values so you can see it better, or just look at your x's and then look at your y's within the set. Decide if it... So from 3 to 5, we are adding 2, 5 to 7, adding 2, 7 to 9, adding 2, 9 to 11, adding 2, 5 to 4, -1, -1, -1. So yes, it is linear. Okay, so given a graph, can you decide whether it's linear or not? Given a table of values, can you decide if it's linear or not? Is that what's different from the Desmos? All right, and then we have our linear equations. So another way to determine whether a function is linear is to look at its equation. A function is linear if it is described by a... How do we know it's linear? So if we look at its equation, what needs to happen to my x?
Oh, it needs to be like singled out.
So another way to determine whether a function is linear is to look at its equation. Think about our Desmos activity. How did I know if the equation was linear or not linear?
It had to be like alone. Like you can't have.
Keep talking. What do we mean alone? X had to have a what?
The house I said.
It needed an exponent of what? Needed to have an exponent of 1, right, on our variable term. So, a linear function, thank you, is any equation that can be written in what we call standard form. So this is what standard form looks like. Standard form is any coefficient a times x plus any coefficient b times y is equal to c, where a has to be some type of real number, and your x, notice, has an exponent of 1, and your y has an exponent of y, and c just represents some constant. So things to notice. X and y both have exponents of 1. X and y are not multiplied together. X and y do not appear in denominators, exponents, or radical signs. So to determine whether something is linear or not, you can rewrite something in standard form, right? So these would all be linears. Notice that my x's and my y's have exponents of 1. They're not being multiplied together. They're not in a denominator. Here I have an exponent of 1 in this y, exponent of 1, exponent of 1, exponent of 1. Again, they're not being multiplied together. They're not in denominators. Over here, this is not linear because it breaks the rule of x and y being multiplied. Does everybody see that? Here I have an exponent of 3, so that's not linear. Here I have a y in a denominator. Okay, so these are things to look for to let you know that it's not linear. These are all good things that do make it linear. So, looking at example 3, is it linear? Yeah. So, yes, linear. Just so we have it in our notes, why is it linear? Well, we know that our exponents of x and y are both 1. And we know that it's not being multiplied together, or they're not in the denominator and all that good stuff. If I had to graph that linear function, what would we do? Well, we would make a table of values where we would pick whatever x values we would want. In this example, the x values that they chose were 0, 1, and 2. I always say pick some negatives, pick 0, pick some positives. It does say you only technically need 2 points to make a line, but graphing 3, so you should have at least 3 points to kind of get where you think your pattern of your graph is going to be. Whenever you are going to be graphing from this point on out, always connect your dots and put arrows on the end of your graphs, please. Don't just leave them as dots. Okay? Why is b not linear? Has an exponent of 2. Perfect. Okay. All right. So now within your group, you need to go through 3a, 3b, 3c, and decide if it's linear or not. 2 out of the 3 are linear. I want you to then graph those 2 that are actually linear. Go ahead and do that. So for those of you who are confused, which one out of the 3 is not linear?
C.
Okay, so let's ignore that one. So that one's not linear. So now if the other ones are, we can make a table of values for 3a. So let's pick 1. So I think if I go in the negatives, I'm going to not be on the grid. So when I plug in 1, what do we get for my output? -4. So then I can plot the point 1, -4 on my graph. Let's go 2. If I input 2 into my function, what's my output? +1, right? Because it'd be 10 minus 9. So 2, 1, I can plot that. If I plug in 3, I'm just making up x values.
Because that makes sense.
So 5 times 3 is 15. 15 minus 9 is 6. So I can plot 3, 6. So that gives me a pretty good idea of what my graph looks like.
Hey, I got that same graph.
So now for 3b, someone give me an x value to plug in. 1. If I plug 1 in for x, what's my output?
112.
It's just going to be 12. If I plug in 2, what's my output? 12. It's just always going to have an output of 12. So 112, 212, 312. So I see a pattern of just being a horizontal line up there at 12. Okay. All right. And then the last part is just putting it into the real world. So for linear functions, whose graphs are not horizontal. Guys, quiet please. For graphs that are not horizontal, our domain and range for any linear function is always going to be all real numbers. How do we do all real numbers in interval notation again? Yeah, negative infinity to infinity would be your domain, and your range would be negative infinity to infinity. So I would make note of that so you remember it. I would make note of that so you remember it. So in many real-world situations, the domain and range might be restricted, right? We talked about how things might just happen in quadrant 1 because it's positive, positive. Graham, question?
Can I go to the bathroom?
You don't have to ask, just go. Make sure you sign out and take a pass. So here we have Sue, who rents a manicure station in a salon and pays the salon owner $5.50 for each manicure she gives. The amount Sue pays each day is given by the function f of x equals 5.50x, where x is the number of manicures. Graph the function and give the domain and the range. So let's make a table of values.
Okay.
What's our first x we could possibly have? Could I do -1 manicures? No. I guess I could do 0 manicures, right? 0 manicures means I'm paying the owner that I'm renting from $0. 1 manicure, I'm paying how much? $5.50. 2 manicures, I'm paying how much? $11. 3, I'm paying $16.50. All right, so that's pretty good. I think I have an idea of it. So we've got 0, 0 down there in the bottom. We've got 1, 5.50. Ooh, where's that about? Like right here, you think? 2, 11. Maybe right about there. And then 3, 16.50. I don't know, estimate it. And then connect with a line. Make sure you put an arrow at the end. Why am I going to put an arrow on the right side of my graph? Because it's just going to keep on going, right? So let's talk about the domain. What's my smallest x that it could potentially be? 0. Can it equal or not equal 0?
Yeah, it could. You don't pay anything.
It can equal. We can do 0 manicures, right? So is it going to be a parenthesis or a square bracket? Square bracket. 0 all the way up to infinity. We never include infinity because that's not a real number, so it's always a parenthesis there. And then my range, what's the least amount of payment I need to do? 0 up to infinity also. So that would be my domain and range. Okay? Questions with any of that? All right, so see if you can do the check it out number 4 on the bottom.